In this module, Module 9, I'm going to give more examples of showing how to simplify and manipulate Boolean equations. So we'll start with a review of simplification methods, and then I'll give a lot more simplification examples. So specifically using T8 prime first when possible, examples of multiplying out and factoring, and then showing how to go from minimized and canonical forms of both SOP and POS forms of equations. Okay, so our simplification methods, we're going to use these methods mostly here: distributivity, covering, combining, expansion, duplication, and what we call the simplification theorem. So let's show an example of using distributivity, specifically T8 prime, in the reverse direction, where we'll go from B or C, quantity and B or D, and turn that into B or C and D. So this is that weird distributivity where the or distributes across the and. B or C and B or D. B or C, quantity and B or D. And not only is it the weird version of distributivity, weird in that we can't use it in the traditional algebra that we've been used to. We can only use it in Boolean algebra, but we're going to use it in the reverse direction. So here's the example that we had from the prior module as a review. We have some term A or another term, quantity and that same term A or another term. So we're just going to use T8 prime distributivity in the reverse direction. I'm going to go in that direction and get A or the and of these two terms, B and C and D and E. And again, as I showed in the last module, we could have used multiplying out where we say A and A, or A and DE, or BC and A, or BC, DE. So distributivity. And then we're going to get A and A, idempotency, or ADE, or ABC. I just used commutativity on that term, or BCDE. And now we're going to use covering. A or A and something is just A, covering, or BCDE. And we end up at the same place. So here we show that we end up at the same place, but more steps, more terms. The second method, again, is called multiplying out. So let's talk a little bit more about this method of multiplying out. It's used to get our equations in the form of sum of products. An expression is in sum of products or SOP form when all products contain literals only. So this is in SOP form, not canonical, but minimized SOP form. This is also in SOP form, again, specifically in minimized SOP form. But it's a sum of product terms, of implicants. This second one in the middle, this one is not in SOP form because each of the terms is not a product. Is an or of something, but it's not a sum and or of products. This is not a simple implicant or product of literals. Okay, so this one is not in SOP form. But we could use multiplying out to turn it into SOP form. Let's show that example here. So I'm going to start with that original equation, y equals df or E and quantity A bar or B. Well, I could use distributivity to distribute that E across those terms. So again, distributivity or multiplying out. So E and A bar or E and B. And now this is in SOP form, sum of products. We have a sum of products of implicants. Here's another example of multiplying out. we want to apply T8 prime first when possible. And again, we're going to apply it in the reverse direction, where we're going to have some term or another term, quantity and that same term, W, or another term. We're going to turn that into W, the first term, or the and of the product of, right, the and of these two terms, X and Z. So we can notice that pattern here. We have some term or something, quantity and that same term A or something. And so we're going to use T8 prime distributivity to turn this into A or that second term, C or D or E, ANDed with this term B. Again, very important to keep the parentheses in place there. So we use distributivity, particularly T8 prime in the reverse direction. And now we can multiply out where we get A or B and C or B and D or B and E. So this is the preferred method, method 1. I'll show the other method of strict multiplying out, and it's going to take more steps, again, more prone to errors because there are more terms and more steps, but as long as it's logically valid, will get us to the same place. So this is the not preferred way. The first way I showed is the preferred method, but I'll show this way to show that it's going to get you to the same place. So we start with our original expression, A or C or D or E. For some reason, we don't recognize that we could use T8 prime. And so we can multiply out. We're going to get A or A and B, or C and A, or C and B, or D and A, or D and B, or E and A, or E and B. Okay, doesn't look the same yet, but so we used multiplying out or distributivity to get there. Now we're going to use idempotency. A and A is just A. So idempotency, or A, B. I'm going to do some associativity here as well, or commutativity. Commutativity to commute across this and. Change C and A into A and C. And use commutativity again to make that B and C. Alphabetic order is going to be easy for our brains to think about. So best to put these terms in alphabetical order. A and D again, commutativity, or B and D, commutativity, or A and E, or B and E. Okay, so I've used idempotency here to turn A and A into A, and I've used some commutativity and some of the remaining terms. And now we're going to notice that, well, A or A and B, that's covering. That will just reduce to A. A or A and C, also covering. A or A and D, A or A and E, those all are covering. So those terms are reduced to just A using covering. And then we bring down the remaining terms, or BC, or BD, or this last term, B and E. And we end up in the same place that we did before. So again, method 1 is the preferred method, where we recognize that we can apply T8 prime first. But method 2, just straight multiplying out, also works, just takes more steps. And again, the more steps you have, the more chances you have to make an error, etc. And here is our simplification method that we just used, written out, method 1 and method 2. And again, this is a case of using multiplying out to turn the equation into SOP form and minimize our equation so that it has the fewest number of implicants. Here are implicants, where each implicant has the fewest number of literals. Now let's talk about factoring. So factoring allows us to get an equation into POS form or product of sums form. So recall that an equation is in product of sums form, POS form, when all the sums contain literals only. So these are minimized POS forms, not canonical forms that we introduced when we first talked about POS equations, POS form equations. So these are minimized. But again, the sum terms need to include literals only, so the true or complement form of a variable. So this is POS form. This bottom one is also POS form. The sums include literals only. That sum includes just a single term. That's fine. This next one, this middle one here, this one is not POS form. Because this one's okay, but this one, this sum here does not include just literals. It includes an OR term that has a product in it. So G and H instead of just literals. We can turn that into a POS form equation using distributivity. So let's go ahead and take a look at that. Let's recall that if we have some term y equals A or B and C, I can take that or, I can distribute across it. We're going to get equals A or B and A or C. So again, this is our distributivity, that odd form, that dual form of distributivity that only applies to Boolean algebra and not the typical algebra we're used to. But we can start with our equation here, this one that was not in POS form, y equals D or E and F bar or G and H, and we can use distributivity to factor that into POS form. So I can take that term, F bar or G and H, and turn that into F bar or G and F bar or H. F bar or G and F bar or H. And then I don't forget to bring down my other term, D or E. And now it is in POS form, minimize POS form. Here we have another example of factoring. So we start with this equation, and you'll notice that this equation is in sum of products form, and minimized sum of products form. And we can apply T8 prime. So we're going to take this and we can associate amongst this and term as we would like. So we can have A or B bar C and A or DE. So we distribute across the or, A or B bar C and, there's our and in there, A or DE. And then we can do the same thing within each of those terms, A or B bar and A or C. And then again, on this term here, we get A or D and quantity and A or E. And now we factored that original SOP form of the equation and turned it into a POS form of the equation using the distributivity theorem, the dual form of distributivity in this direction. And here's that process again, typed out for your convenience. Note that we didn't have to do this, but for you to recognize that we can treat those terms as a single term and then use the same principles that we did here with our distributivity theorem, you could substitute variables x and z in for b bar c and d and e, respectively. So x equals b bar c and z equals d and e, or not. You don't have to do that step, and we didn't do that step in the prior example. But if it helps you, go ahead and do that. And once you've seen this, you may realize that you can go directly from y equals a or b bar c and d and e, and we can distribute across that entire term and turn that into a or b bar and a or c, so a or b bar, and a or c, and a or d, and a or e. So here's another example where we can apply factoring or distributivity, T8 prime, to factor this term by distributing across the or. So we have some term here, a, b, or c bar, d, and e, or f. Well, it doesn't look exactly like we did before, but we could start with, for example, we could start with this term and factor across that term. So we could say a and b, this term, or c bar, a and b, or c bar, and a and b, or d, quantity and a and b, or e. So we distribute across that or, again using T8 prime. And we don't forget to bring down our other term, or f. And now, well, it's almost factored, but not quite. So we can see, well, we can distribute this way. We can get c bar or b, quantity and c bar or a. So again, we take that term and turn it into c bar or b, quantity and c bar or a, and take the next term and turn it into d or b, quantity and d or a. Now we take the next term and turn it into e or b and e or a. And then we don't forget to bring down our other term, the or f term. And now we have something that looks kind of like what we had. So we have f here, f, or a bunch of things ANDed together, a bunch of terms ANDed together. They're not literals, but they are terms that are ANDed together. So now we can distribute that or across each of those AND terms. So we can say f or e or a, quantity and f or e or b, quantity and f or d or a, and so forth. So we get this f distributed across the or. We get f or c bar or b. I'm distributing that across this term. Quantity and f or c bar or a. Quantity and this next term, f or d or b. Quantity and f or d or a. Quantity and, put these down here, f or e or b. Quantity and f or e or a. And then we can rearrange those terms in alphabetical order. So we'd get this term b or c bar or f, ANDed with a or c bar or f, and so forth. Just putting those sum terms in alphabetical order. ... And here typed out for convenience. So here we have those terms now in alphabetical order. And we've turned using factoring, using TA prime, we have turned this minimized SOP form of the equation into a minimized POS form of the equation. And again, that process going from SOP to POS using distributivity is called factoring. Now let's revisit our SOP and POS forms, both canonical SOP and POS and minimized SOP and POS. And then we'll talk about going between these two forms. We've really already gone from canonical to minimized, but we can go either direction, from minimized to canonical, or the other direction, canonical to minimized. So let's review our canonical SOP forms of equations, and this is the initial SOP form that we talked about. So canonical SOP form is when each product contains the true or complement form of each variable. So these products we had a special name for them called minterms, where those minterms included a true or complement form of each variable. Canonical POS form is a product of sum where each sum contains the true or complement form of each variable. So the sum, we had a special name for that, which was a max term. So let's revisit some examples from canonical SOP and POS form. So in this slide, we're talking about the canonical forms. So we have some expression, some function, E, the output E, that has ones in the 0, 0 case and the 1, 0 case. Our inputs are O and C. The letter O, that's not a 0, that's the letter O. And so again, for sum of products, for canonical sum of products, we look at where the output is 1, and we include those minterms in our equation. So E equals O bar C bar, the minterm 0, or O and C bar. And so this term, O bar C bar, will force the output E to 1 in the case that O is 0 and C is 0, because that term will be 1. And then we OR it with another case we want the output to be 1. Well, in the 1, 0 case, we also want the output to be 1. So this minterm, O and C bar, will force the output to 1 in the case that O is 1 and C is 0. And we can also write this in shorthand form. This is equal to the summation of minterm 0 with minterm 2. So here's our minterm 0 and minterm 2. Again, if we want to manipulate these equations, though, we need to write it in our longhand form. We can also write functions in POS form, in canonical product of sums form. And in that case, we're going to circle where the output is 0 because we're forcing the output to 0. And we're going to include the max term associated with each of those rows where the output is 0. So each of those max terms is going to force the output to 0. They're in an AND relationship. So this term here, max term 0, is false when O is 0 and C is 0. So we include that in our equation. E equals O or C. That term will force it, that max term will force the output to 0 in the 0, 0 case. We get 0 or 0, that will evaluate to 0. We'll get 0 and whatever. Anything in an AND relationship where there's a 0 as one of the terms will evaluate to 0. And we also include the next max term, O or C bar. Well, that term will evaluate to 0 in the 0, 1 case. In the 0, 1 case, we'll get 0 or 1 bar, which will be 0 or 0. That will evaluate to 0 in the 0, 1 case and force this output E to 0. And finally, the last term where the output should be 0, we're going to get the 1, 1 input combination. And so that max term, O bar or C bar, will evaluate to 0. And in this AND relationship, we'll get 0 and something. Turns out those are both 1, but we're going to get 0 and something will force our output E to 0. So again, in product of sums form, in canonical product of sums form, we're forcing the zeros. We're forcing the output to 0. And we can also write this in shorthand form, the product of max terms 0, 1, and 3. So 0 here, max term 0, max term 1, and max term 3. So we also could have written this function in sum of products form. That would have been, well, we would have circled the 1s, and that min term associated with this row, the min term would be, regardless of what the output is, O and C bar, because we have a true form of O, the complement form of C, in order to make that product term true. O and C bar. So we'd get E equals O and C bar. This is the sum of products, the canonical, and turns out minimized sum of products form to represent that function. So the question is, we have these two equations, one in POS form, in products of sums form, and one in SOP form. And we claim that they're equivalent, and in fact, by perfect induction, we can show that they're equivalent. For every input combination, the output evaluates to the same value given either equation. And so we can also now use Boolean theorems and axioms to manipulate the equations to make them look like each other, to prove that they're true using Boolean algebra. So let's go ahead and do that. I'll show the simplest method first. So let's start with the POS form and try to turn it into our SOP form. So we're going to try to make the POS form using Boolean algebra to try to make it look like O and C bar, the SOP form. And we can use combining to combine these two terms. This is an example of combining, and particularly the dual form of combining. So O or C quantity and O or C bar is the same as just O. So we can take that and make that just into O. And then we don't forget our last term, that O bar or C bar. And now we get O and O bar or C bar. Well, we can use distributivity to distribute that O across the and we get O and O bar, or O and C bar. O and O bar evaluates to 0. The common mistake here is to say, oh, O and O bar, so a variable ANDed with its complement is 1. Well, that's definitely not true. So this is the common error, but in fact it's not equal to 1. People want to make it equal to 1. That's not right. It is equal to 0. And the value is 0 because, well, either O is going to be 0, then we have 0 and something. Anything in an AND relationship with 0 is going to evaluate to 0. Or O is going to be 1, and its complement is 0. So one of those terms in that AND relationship is going to be 0 no matter what. So we'll have 0 in an AND relationship, and that will evaluate to 0. So O and O bar evaluates to 0. We get, using the complements theorem, we get 0 or O and C bar. 0 or anything is just that anything, using the identity theorem. And then we just get O and C bar. And there are other ways that we could have gone, other steps we could have taken using Boolean algebra to show that those two expressions are equivalent. Let's now talk about converting to canonical forms from the minimized form. So we're going to use the combining theorem, but we're going to use it backwards. So up until now, we've kind of started with a more complex equation and simplified it using combining in this direction to reduce the number of terms, to minimize the expression. So we could, for example, start with a canonical sum of products form and then use combining to convert to our minimized sum of products form. But now suppose that we want to go from the minimized form to the canonical form. Well, we can still use combining theorem, but we're going to use it in the opposite direction. We're going to take a term and expand it using combining, and we're going to use this form, the T10 form, for sum of products. We're going to use this form for product of sums, the dual form for product of sums. So let's show an example of converting to canonical forms, and particularly let's start with converting to canonical SOP form from a minimized SOP form. So let's start with this minimized SOP form, and we want to convert it to a canonical SOP form. So first we need to know how many inputs there are. So we can know, for example, that y, just because I tell you that, somewhere you figure out either by your own design or someone tells you. In this case, y is a function of 3 inputs, a, b, and c. And so now we want to use the combining theorem to expand this expression. So we can go from y equals a, use combining to say, well, a can expand to a and b, or a and b bar. So I use combining, but in the reverse direction, y equals a, and I turned that into a and b, or a and b bar, because I knew I needed a b term in my expression. And now for each of these terms, each of these product terms, I need to include a c term, because c is also one of the inputs. So now I can use combining again and get a and b and c, or a and b and c bar. So here's my original a and b, and I ANDed it with a true form of c, a complementary form of c, and then ORed those terms together. So again, combining, I took a and b and turned it into a and b and c, or a and b and c bar. Now I take this next term. I also need to include a c term, so I use reverse combining, a b bar c, or a b bar c bar. And now I can write this in the order of the minterms. So this would be 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this would be minterm 4, minterm 5, minterm 6, and minterm 7. So I'll write it as A and B bar and C bar, or A and B bar and C. Now I've taken care of these two terms, using commutativity to move these around. Or this next term, A and B and C bar, or the last term, minterm 7, A and B and C. Why do I bother writing it in canonical form with the minterms in the order? Well, again, uniformity and regularity, just to make sure that I have it correctly. So for example, I could even put this into a truth table to double check. Well, let's see, we have A and B and C, and output Y. So we have all possible combinations of A and B and C. And I can see that, in fact, the output Y is going to be true whenever A is true. So it's going to be true in these cases, in these rows, and not true in the rest of them, because A is false in the top 4 rows. And so, in fact, we do want to have 4 minterms in our expression. This is a double check. Minterm 4, minterm 5, minterm 6, and minterm 7. Okay, so I converted from minimized SOP to canonical SOP form using basically the reverse method of what we've been doing to minimize equations. So I've used combining in the opposite direction. I've turned A into A and B, or A and B bar, where when we're minimizing, we go in that direction. and take the two terms A and B or A and B bar and reduce them to A. So here's another example of the combining theorem. Here we have some expression in minimized SOP form, minimized sum of products form. So we have a sum of products. But it's minimized because we can already tell that because each of the product terms is not a min term. That is, for example, in this term, the C, either true or complement form of C is missing. In this term, the true or complement form of both A and B are missing. So again, we can use the combining theorem. Normally we use it for minimization in that direction. In this case, we can use it in the other direction where we expand A and can add variables into our terms. Okay, so we start with y equals A and B, or C bar. Again, write that as a bar, not a tick. And we could start with this term and say, okay, well, I need to put a C into that term, so I can expand it using combining. So turn that single term A and B into A and B and C, or A and B and C bar. And don't forget to bring down our or C bar. And if I want, I can go ahead and start using reverse combining on that. For example, let's put our B variable into that, or B and C bar, or B bar and C bar. And now in each of these terms, we need to add in an A term. So for that B and C bar term, we get A and B and C bar, or A bar, complement of A, and B and C bar. And for the B bar C bar term, we get or A, true form of A, B bar C bar, or the complement form of A, and that same term, B bar C bar. So we've expanded B bar C bar into those two terms using reverse combining, and B and C bar into these two terms using reverse combining. And now we don't forget to bring down our first two terms of the expression, A, B, C, or A and B and C bar. And now we notice that this term here, A and B and C bar, we have a duplicate of that. So remember our idempotency theorem, where if you have X or X, that's the same as just X. So I can get rid of one of those terms using, again, idempotency. And so we'll get A and B and C, or A and B and C bar, or A bar, B, C bar, or A, B bar, C bar, or A bar, B bar, C bar. And now we can reorder them in min-term order. And if it helps you, you can write down the row associated with it. So 0, 0, 0, 1, 0, 0, 4, 0, 1, 0, 2, 1, 1, 0, 6, and 1, 1, 1. So we get min-term 0, min-term 4, min-term 2, min-term 6, and min-term 7. So now we can reorder those and say, well, min-term 0 goes first, A bar, B bar, C bar, or min-term 2, A bar, B, C bar, or min-term 4, A, B bar, C bar, or min-term 6, A, B, C bar, or min-term 7, A and B and C. And here it is written out, similar progression of steps using reverse combining, expanding the terms using combining, and then getting rid of the duplicate term here, and writing it in min-term order. Min-term 0, min-term 2, min-term 4, min-term 6, and min-term 7. So here's another example of converting to canonical SOP form. We're going to get y equals a and b bar, or c. This is in minimized SOP form, and we want to go to canonical SOP form. Again, we're going to use reverse combining. So this term, a and b bar, is missing the c term, equals a and b bar and c, or a and b bar and c bar. So I've expanded that single term a and b bar into two terms using reverse combining, and we can start using reverse combining on that term as well, or b and c, or b bar and c. Okay, so we expanded that c term into two terms as well, and now we just bring these first two terms down, and we can now expand into the a variable as well. Instead of just BC, we get A and B and C, or A bar and B and C, or A B bar C, or A bar B bar C. And let's go ahead and write these down here so we can see them all in one place. And we check for duplicates, and in fact, if at this point you wanted to reorder them, you would also see the duplicates. So I'll show a different method just to show different ways of doing it. This is our 1, 0, 1 minterm, or 5 minterm. This is our 1, 0, 0 minterm, or minterm 4, 1, 1, 1, minterm 7, 0, 1, 1, minterm 3, 1, 0, 1, minterm 5, and 0, 0, 1, minterm 1. So just by numbering them, abstracting away details that aren't important, I can see that minterm 5 is a duplicate. I can just keep one of those minterms. And now I can reorder them. We'll start with minterm 1 here, A bar, B bar, C, or A bar, B, C, or just going in order here, minterm 4, A and B bar and C bar, or A and B bar and C, minterm 5, and the last one, minterm 7, or A and B and C. Now let's double check that I didn't miss one of my minterms. I count these. Let's see, we have 1, 2, 3, 4, 5 minterms. We wanted to have 1, 2, we'll not count that first one because I X'd it out as a duplicate, 1, 2, 3, 4, and 5. So kind of redundancy check, make sure we have the right number. And then another thing we can do is we can go to the truth table and see if we have the same function as we originally had. So A and B bar, or C. So let's go ahead and write out a truth table for this expression, A and B and C. And now we want to see where each of these product terms forces the output y to 1. So A and B bar is going to force the output to 1 when A is 1 and B is 0, because the term A and B bar will then be true. We'll get true, 1, or something, C, while 1 or something is just 1. So A is true here in these 4 rows, and B bar is true, so B is low, so that B bar can be true in those 2 cases here, 2 rows. So these are the 2 rows where A and B bar is true. And now we look at the next case. Well, we want to see where C is true. C is true in this row, this row, this row, and that row. So we get 1s in each of those rows because the or C or 1 will force the output y to 1. So here we have our 1s, and we can fill in the rest with 0. So now we can check. Well, let's see, we would have minterm, this would be minterm 0, minterm 1, not minterm 2, minterm 3, minterm 4, minterm 5, not minterm 6, and minterm 7. So let's see, we had 1, 3, 4, 5, and 7. And we could also write this as sum of minterms, 1, 3, 4, 5, and 7. So a couple of redundancy checks that you can make at the end. If you have time, on homework, I'd recommend it. Get full credit. On an exam, come back to it and do the redundancy checks if you have time. So now let's do some examples of converting to canonical form for POS form equations. So again, we're going to use reverse combining, but we're going to use the dual form A is equal to A or B quantity and A or B bar. So let's suppose that y is some function of, if it were just A and B, so you kind of need to know how many inputs it has, but let's suppose it were just a function of A and B, well then I can just expand A, this term, into exactly what I've written over there to the right, A or B, and A or B bar, and now we have our canonical POS form. If instead y were some function of 3 inputs, A, B, and C, then we could have, well, we'll start with that step above, A or B, and A or B bar. Now, in each of these terms, we need to include a C, so I can expand that into, well, the original term, or C, and the original term, A or B, or C bar. So the original term, or C, ANDed with the original term, or C bar. Same principle of combining or reverse combining. Now we take the next term, A or B bar, and expand it. Can I just do that? Nope. That's not true. That's not logically valid. I just included half of combining. That's not correct. I have to include both sides, A or B bar or C, and A or B bar or C bar. And now I can check and see if I need to reorder these. Well, let's see, this is the 0, 0, 0 max term. Remember that for max terms, the sum term is false for that row. So if I have the true form of a variable, it's the 0 value of that variable. It corresponds to the row where B is 0, A is 0, and C is 0 in this case, because we have true forms of each of those variables. So we have the 0, 0, 0 max term, otherwise max term is 0, 0, 0, 1 max term 1, 0, 1, 0 max term 2, and 0, 1, 1 max term 3. So in this case, we don't need to reorder it, and here we've completely and correctly gotten the canonical POS form from the original equation using expansion, using combining, or specifically reverse combining. And again, we can double check. We could have written this in shorthand form as the product of max terms 0, 1, 2, and 3. Write a truth table, A, B, C, and we have ones where A is 1, so A is 1 in those 4 rows, we have ones on the outputs, and 0 in the rest. And in fact, these zeros, the max terms corresponding to those rows where the output is 0, those are the max terms that we include in our equation. So indeed, max term 0, max term 0, max term 1, max term 2, and max term 3. So again, did a double check to make sure that there wasn't some error in a step. So here's another example of converting to canonical. Well, we could do canonical SOP form, but let's go ahead and do canonical POS form. So we're going to use reverse combining like we did in the prior example. But first we're going to use distributivity to distribute that C across the OR. So we're going to get C or B bar and C or A. So we started with a minimized SOP form. And so first thing I can do is to get the OR, or the sums, the OR terms, by using distributivity across OR. If there are no OR terms like there are here, we can just use reverse combining like we did in the previous example. But because there's that OR there to start with, we go ahead and use it to our advantage to get our initial sum terms or initial OR terms. And I can rewrite this so that it's in alphabetical order, B bar or C, just using commutativity, and A or C, commutativity across those OR operations. And this would be, in fact, minimized POS form. So that's another way that I can convert from sum of products to product of sums, is to use distributivity or factoring to convert to our POS form. But now suppose we want to take the next step and convert this to canonical POS form. Well, this first term, B bar or C, I have to expand that using reverse combining. I need an A term in there, so we're going to get A or B bar or C, the original term, ANDed with the complement of A or B bar or C, and AND that with the next term. We need a B term in that, so we're going to get A or B or C, ANDed with A or B bar or C. So now each of our sum terms or OR terms includes either the true or complement form of each input, but we now need to double check and make sure that it's in the correct order. So we can go ahead and check which max term this is. This is the 0, 1, 0 max term, so the max term 2. This is the 1, 1, 0 max term 6. This is the 0, 0, 0 max term 0. This is the 0, 1, 0 max term 2. And so if I wanted to write this in shorthand form, I would write it's the product of max term 0, and I notice now that I have duplicates. Max term 2 was duplicated, so I can get rid of one of those terms in my expression. So max term 0, 2, and 6. And we can double check that with our truth table. We'll do that in a second. But let's go ahead and write out the longhand form of this. So max term 0 is going to be our A or B or C max term, ANDed with max term 2, A or B bar or C, ANDed with max term 6, A bar or B bar or C. So here we have our truth table with our inputs A, B, and C, and our output Y. The original equation was Y equals A and B bar or C. Well, A and B bar is true here, where A is true and B is false. And the C term is true, so or C. That's the other case that the output will be true, is in these rows. So 1, 1, this 1 was already there. So that one is being forced by two terms, by both the A and B bar term, as well as the C term. And then we have zeros everywhere else. So first check is, we have 3 cases, 3 rows, or 3 input combinations where we'll get zeros. So it's good that we have 3 max terms here. And the max term that we should have in our equation is max term 0, max term 2, not 3, not 4, not 5, but max term 6. So check. We double checked with our truth table, and in fact, we didn't make any logical errors in our steps. You'll notice, let me point out again, that our product of sums form and sum of products form are complementary. So if we were writing this in sum of products form, canonical sum of products form, as we did in the prior slide, this would be Y equals the sum of max terms 1, 3, 4, 5, and 7. So all of the ones that weren't included in our POS form. So 1, 3, 4, 5, and 7. So that's another check. If your product of sums form and your SOP form are not complementary, that is, there should be no row that is included in both POS and SOP form. If that's true, then there's some error that you made in one of your steps. So there's another redundancy check that you can make, that these terms here that are included in the POS form and the SOP form are complementary. And again, POS, this is the canonical POS form, and this is the canonical SOP form. So our topics in this module, again, were to review our simplification methods and do some more examples with simplification. We showed that when possible in simplifying, it's best to use T8 prime first, if it's possible. And then we showed ways of multiplying out and factoring. Factoring is useful in turning equations into POS form, and multiplying out is useful for converting equations into SOP form. And then we also talked about and revisited canonical SOP and POS forms and minimized SOP and POS forms, and talked about converting particularly from minimized form to canonical form. And then we can also go back from canonical forms to minimized forms of SOP and POS equations.